Is my voice audible?
Yes.
Hello? Am I audible? Okay, I think I
You
cannot
are
hear.
audible
Just a
still.
minute. Yeah, can someone just again confirm? Am I audible or not?
Yes, sir.
Yeah, I can hear now. Fine. Okay, so this is week six open session. I would discuss the concepts of week six, but before discussing the concepts of week six, do you all have any doubt in the topics which for the quiz one?
Can you please discuss recurrence once? Time complexity and recurrence.
Recurrence, do you have any specific doubt? So see, recurrence is you just have to do, I mean, in your syllabus, all you have to do is just substitution and solving. Okay, so you don't have much other than that.
Quick sort.
Just you have quick shot.
Yes, I was actually unable to understand the logic.
Okay, so quick shot, if you go for, by the way, quick shot is not there in your first quiz, right?
It is.
Is it there?
It's in week 3.
Oh, acha, sorry, in week three, correct, yeah. It's in week three. Fine. Okay, so quick shot, how it happens is, wait, let me write it. Just a minute. My screen is visible, no?
Yes,
Yeah,
sir.
yeah.
Okay. Okay. Yeah. So, quick shot is what we generally do is actually the whole week has multiple improvement in the quick shots. Initially, we learned quick shot, which takes order n squared time, and then after that, we go for better approach, right? And that approach requires you to find the kth element, kth largest or kth smallest element in a list uh, in less time. And then finally, still we saw that even by finding kth largest element, it may take order n squared time. So you actually go for median of median. So essentially, what happened in quickshot? So basically, if we look at the how quickshot works is, so I would just broadly write the pseudocode. So let's say we have one quickshot method, right? And the parameters are over here. Fine. And then inside the quickshot method, what you do is at first you check if your beginning less than end, then only you do whatever you have to do. And at the air, you actually apply k equal to, you call for a partition, the partition algorithm. Right now, this partition algorithm in the lecture, it is actually, I mean, in the code, it is put both together. I mean, it's not separated out. The whole thing is actually put inside a single code. I would go to that code, but here, for the sake of explaining, I'm writing it like this. So what this partition is basically doing is the partition method over here. It's defined over here. The partition method's task is to find the correct position and place the element which I pass into the partition method into its correct position. So what do we mean by placing into its correct position? That means, let's say if you have an array, right, and we pass an element, and that element is the first element. So that is what we call the pivot element. Okay, I would not go into line by line details of the things because those are there in the sessions. So, but yeah, so you have the pivot element over here, and then what you do is with this pivot, you check the consecutive next elements. Whatever are the next elements, you check with the first element, which is your pivot. And then you find that if this element, right, the first element that you are comparing with the pivot, if that is a smaller element, then you proceed further. If it is a larger element, then you do the swap. So at the end of the day, what you basically get is, if you repeat this process for the whole array, what you get is you place the pivot over here, right? So let's say the pivot over here was 7. So you place the pivot over here at its correct position in the array. Now, so all the numbers on the left hand side of 7 are lesser than 7, and all of them which are on the right hand side would be greater than 7. But this is not sorted order. So this would be unsorted. I mean, the numbers lesser than 7, but obviously they are unsorted. Right, and likewise here also. So only work of partition algorithm is to place the current pivot element, which is the leftmost element or the first element of our array, into its correct position in the sorted list. I mean, assuming that in the sorted list, wherever the correct position of the pivot element is, there you place 7. Fine. And what is k? K is basically the index which partitions return. So this is k, the index of the array where 7 has to be, I mean, the current pivot has to be placed. Fine. So you put k equal to partition, and once you get the position, you go for quick shot, I mean quick QS, or method name is QS. So you just if I see this part, I mean only this cell, obviously it is trivial because there is a single cell, but this single cell is placed at its correct position in the sorted array, right? So whenever the array is sorted, 7 would not move, 7 would be at its position. So I can look at this element itself as a sorted array of one element. I mean, this part is itself trivially sorted and the array size is of 1, right? So again, if I apply the same logic on the left hand side and right hand side accordingly, then one by one I would recursively, this is why it is called divide and conquer. So dividing, and at every step you are actually putting the element at its correct place. So I would get again a proper element over here, then a proper element over here, and accordingly you at the end of the day you would sort the whole array. So how the function actually grows is the first array you pass, right? The whatever your array is, and then you pass what? The starting position. Now we got the k position, right? So we have to sort on the left and right hand side of k. So that would be from my beginning to k minus 1 and again the array and then k plus 1 to end, and that's it. This is your recursive, your recursive call. And in the partition method, what you do is basically, right, partition, you pass the beginning and the end, right? I'm not writing the whole partition method, but basically you travel, you keep two pointers I and j, right? In the lecture it has been discussed, and you compare, you use the I pointer to compare the current element. So let's say this is my current element, you compare the current element with the pivot element. Now if it is smaller, you increase I and proceed further, right? And likewise, if it is not, then you swap, so that every element on the left hand side of the pivot element remains smaller and all the element on the right hand side of the pivot element remains larger. So if I go to the code and just briefly discuss once. So fine. So the partition which I was saying, this is actually from this line, right? Your pivot lower upper, right? Whatever pivot lower upper equal to L plus 1 R from this line. I mean, after your if and return from the this line, pivot lower upper till your this line, lower equal to lower minus 1. This is your partition algorithm. Okay. So this lines of code, what you that you have these two pointers, lower and upper. You proceed using them one by one, compare it and increase. Whenever there is a greater value, you swap accordingly. Those things are discussed. Just watch the session when we discuss this big shot, right? And this is your recursive call. As soon as you get the L position, right? The lower position where you are actually getting the index. So from you go from the beginning, which is your L. Here you see the beginning is L, right? And R is the end. So from there you go towards K, or K is lower over here. The example that I took over there, K, right? So K is lower over here. So L to lower and lower plus 1 to upper. That's it. There is nothing much in it.
Yeah.
And if you ask, one problem is rather that the corner case, so questions might come that what would be the running time of quick shot when the input, your array input is, let's say this, you have to sort it. Fine. Now you see that we actually use the pivot as the first element all the time, right? And you see that this is always, we don't need to, swap anything. It's always, it is already a sorted sequence, right? Likewise, if I place a, let's say, if I give you a array like this, which is already sorted, okay, or let's say an array like this, which is in the opposite direction. So in all these cases, when you consider them as the pivot element, right? What happens in this case? We do not need to move. In this case also, we do not need to move. In this case, we would move, but what we would do is we would place it at the end, right? So our array would be, assuming we are sorting in the, in ascending order. So whatever element I am not writing because this would not be the proper sequence. At the end, 6 would be there. So what is happening in all these three cases? How much decrease in array size happens in the next iteration? So we were planning that we would place, like here we place 7 in the middle, or at least some position after the start, and we actually got the 2 segments of the array like this. So this was actually helping you to getting the recurrence to Tn by 2 plus order of n, right? So this 2 Tn by 2, right? Because we have divided the array. As soon as you place this would not always be 2, this would be some factor. But if you exactly, so let's say if there are elements 1 to 14 in this array, right? So then 7 would be the middle element. But even if it is not, let's say I get 2t n by some factor, let's say I call it beta, right? That also is sufficient enough. I think those things are discussed in the session, why it is sufficient enough. Because this factor would directly go into the complexity of order of n log beta base n, right? This is your actual term. Now, asymptotic complexity, we discussed that constant does not matter. So I can write this statement like order of n log n, right, base 2 by log beta base 2. Now you see this is a constant term because beta is constant and 2 is also a constant. So I can take this thing out of the picture simply, right? So I am removing it. So you get n log n. So the factor which is in the base of logarithm, that is actually this factor, right? The amount by which you are dividing the array. And that does not matter because asymptotic analysis does not take that in concern. So this beta factor we don't have to care about as long as it is it is some place after the first element. It is somewhere in the middle. But if it is not in the middle, then the problem we get is, so in all these 3 cases I discussed that. The problem is now we are not dividing the array into 2 parts. We are placing the element in the end only. So here in the left end and here in the right end. So the array that we get over here is n-1 size, right? In all these 3 cases, we get an array which is of n-1 size. So this is not equal to our sum 2t n by beta, right? There is no concept of this 2. We are not able to divide it, right? So in this kind of scenario, our recurrence relation actually boils down to the t of n equal to what happens? We only got the array which is 1 less in size, right? So t of n-1 plus order of n, right? Because this is our n-1 size. So this is our new recurrence. And if you simply substitution, so one of you said that recurrence relation, right? The recurrence solving is very easy. What you do is simply substitute. So let's see, if I take this for example, t of n-1 plus order of n, right? So I can back substitute it, and what I would get is, so in place of t of n-1, if I put over here, right? So what would I get? Right, t of n-1 equal to t of n-1 minus 1 now, right, plus order of n, which is n. I'm writing it as n over here. So I'm sub n-1 plus the n, right? Why n-1? This part is basically because of the substitution. This is equal to this part. Okay, and plus order of n is this one over here. So after that you simply do that. So you get t of n-2 plus n-1 plus n. So you can see that this at some time it would go to some form like t of n-k plus what? N minus k plus 1 plus dot plus n. Okay, and at some point it would become 1, right? Because let me add a few more dots. Yeah. So we are decreasing it. Now when will this t of n minus k, my base case condition, right? When k is equal to n, what would happen? When k is equal to n, I have reached the end of the array. A single element, I'm breaking by 1. So every step I'm getting a size of n-1, right? So n-1, n-1, n-1. At one point I would reach the end of the array, and that time I would get a single element. So if I put k equal to n, you see that this term is actually becoming 1, right? So our recurrence actually becomes, then if I remove this, so this would become 1, and our n minus k, what would happen to that? We know that this would be t of 0, which is some constant type, right? I'm writing is some constant plus 1 plus dot up to n. Now you all know what this value is. Actually, this is not n. Yeah, here n only. Yeah. So obviously, that would come your AP summation n into n plus 1 by 2. This is the order of n square. Right. So this is how you solve recurrence. Now some recurrence might come in your examination, right? You have to maybe simple recurrence might come. I mean, you have to just think. Let's say we give you log n. Okay, log n log n square. Fine, and let's say. Okay, anyways, these are quite nice. So you can maybe we ask you that which of these following are the, or let's say another is 2 to the power. Okay, 2 square, or let's say 2 to the power n. And we ask you which asymptotic function is, I mean, select the proper sequence where the asymptotic functions represent the increasing order of growth. Right. So if I see over here, which one would be the smallest one?
Log n.
So this would be my smallest one. Okay, fine then.
Log n. Log n
Fine.
square.
Okay.
2 power log.
What is this, by the way?
Log
Log n square, right?
log n.
Sorry, what would be
2 log n.
2
power
log n?
2 log n. 2 power 2 log n.
Okay, so 2 power 2 log n. Anything else?
Simply n might.
How can you get n?
Actually, base and power are same, so it will be simply log.
Shouldn't it be n square?
Sorry,
This second last term shouldn't be it n square,
how can you get n square?
because
Two
the
log 2 base. It's right. It get cancelled, right?
I think it's n square.
N square, if you how can you get n square? You have to tell, right? How are you getting?
Because when we used to write e to the power log e log base e and then something, then that something would be the final answer.
Okay, see. So if I just try to break it down, let's say y equal to 2 to the power 2 log n. So this is easy, right? We are just simply putting the exponent according to the property of log. So y equal to 2 to the power 2 log n, right? And if I have to remove, let's say I somehow plan to remove these two. So what I can do is I would do log y, right? So what I get is 2 log n, right? And then a log 2 would be there. So let's say this is base 2. So again, I would get a log 2 base 2. Now this is cancelling out. So I get 2 log n. Fine. Can I simplify it any more? Anything? I mean, can I do? I have to find the value of y in some other terms, not in this form. So what you can do is, let's say you divide it by log y by 2 and then again take 2 to the power, but it doesn't matter. It would not end up you anything. It would not give you anything. Only thing is, if I remove this 2, this is the term you have to consider, 2 to the power 2 log n. But if I remove this 2, then what can happen? Then this 2 would not be there, right? Right. So then if I write 2 to the power log n, right, and let's say y, then simply what you can write is this 2 can go up. I mean, n to the power log 2 base 2. This is base 2 anyway, right? This can be interchanged. Now what you get from here is n to the power 1, which is n. Right? So if I give you this function, then this is nothing but n. Okay. But otherwise you cannot simplify it. Anyways, so after that, this is your next bigger number 4. Okay, because anyway it is logarithmic term and this is direct. I mean, it's 2 to the power logarithm and it is, I mean, if you consider n, then also it is larger. And if you consider the previous example, this n square, right? Then also it is 2 to the power logarithmic term, and this is 2 to the power normal polynomial term. So this would be larger, right? So this is 4 and this is 5. So these kind of questions might be asked, or yeah, nothing, or maybe some code would be given to you, like the mock you have seen now. One code was given, and some you have to find out what is the time complexity for that code. Something like that would come. Yeah, quick shot. Any further doubt? Anything else? I would not go through the iteration steps because I expect you to, see that in the proper discussion for that corresponding week. But this is the overall thing. Okay, fine. So any other doubt? Anything regarding BFS, DFS?
Be live streaming, so I just started recording session. Okay. Yeah. So, so this is the first.
Sorry, I couldn't hear you. Are you saying something? Someone is saying? Okay, fine. Okay, so no more doubts, right? Great. Let us discuss one or two questions in general. So just verbally.
I just have a doubt.
Yeah.
There was one in the old question paper, I don't remember, but I want to ask this question. What is the time complexity of binary search in a linked list?
Okay.
It is
So
related to
let's
that, but I now, as of now, I have to search. But I want to know this because this is related to this question.
No problem. Got it. Sure. So what is a linked list? Now I am again just discussing that because the list and linked list are two different things, right? That point is clear because
Yeah.
so list in Python is kind of an array. I mean, not exactly array. It's a intelligent, what should I say, a workaround of array. But it works like an array list in Python. But linked list is totally different. We have to deal with pointers. I mean, those memory addresses, pointers, and then accordingly we have to work out. So linked list, the main problem is they are not direct accessible, direct addressable. Direct addressable. Now, what do I mean by direct addressable? That is, I cannot write something like linked list of 4. It doesn't matter. I mean, this can happen in an array, but I cannot write this. If I have to go to the 4th node, right, in the linked list, then what I have to do, actually the 5th, because if I consider it an array, then it would be the 5th cell, correct? 5th cell. So if I have to go to the 5th cell in a linked list, so I have to at first have a counter, right? Counter equal to, I have to set it, let's say 5, right? And I would go till 0. And again, I would have a while loop, while a pointer initially, let's assume that PTR was initially initialized with the head pointer, while PTR not equal to none, we would simply traverse the list. PTR equal to PTR next, or whatever the name of that next pointer is, and we do count minus. Fine. Sorry. Not PTR equal to none. This would be count, right? So while my count is greater than 0, right? So you can just think whether I think I might make a mistake in the last condition, whether it is going up to 0 or 1 more. So you can just adjust that. So you have to initialize with 4 or something. But just think about that. But basically the thing is that I have a loop. I would start from the head pointer. I would proceed till, one by one towards the the ith node. But I cannot write direct address, right? Now what happens in binary search if we discuss? In binary search, what do? We actually see
middle element and then
correct. If a mid is equal to the key element, then you simply return. That is, you got, let's say you return the position where you got, so you return mid. Okay. Or if it is not, then you can write that if, right, my a mid is greater than key, then I know that my element, the key element, is actually smaller and it is on the left hand side.
Yeah.
So what you do, you keep the beginning same, you change the end pointer, end equal to mid minus 1, right? And if it is not the case, let's say you go for an else, you go for beginning equal to the other case, beginning plus 1, sorry, mid plus 1. Right, you do that, and at the end of the everything, you just simply, I mean, if you put it inside a loop, then you can use a loop. You can also do it using recursion, whatever manner you want to, right? But the crux is this part, right? Now see what you are doing over here, and over here, obviously those lines would be there that you beginning plus end by 2 equal to mid, all those things. But basic algorithm is this part, and you are using like this, right? A mid over here. You're directly calling it direct access.
Yeah.
Now, every time if I do it on a linked list, this is an array, and that's why you can write this statement. If I do it on a linked list, can I write a mid? No, right? I have to travel. So every time I write, yeah, every time I write this, I have to travel from start, travel from head till how much? Now, see, you know the length of the array, right? So you do initially initialize length by 2 equal to count, and like I did from here 5, you just do it by length by 2, and do count minus minus. So whenever you reach count equal to 0, that is your middle element. Now, how much time did that take you? It would take you a time of order of your length of the array, right? Length of the array by 2. Now, length of the array is nothing but our n. So order of n by 2. So constant doesn't matter. So order of n.
Okay.
So a bit, which you could do in case of an array in order of 1 time, right? So this is now taking you order of n time.
So the overall complexity is order of n. Is that
correct? Huh? So you have to do this order of n work every time. Right? Actually, see, it's not only order of n. So let us see this. So if I do this a mid equal to p, this is taking order n time, right? And let's say I do not get it, and then again I recurse again. So how many times you are going log n time? I mean, you are doing that middle thing, that is correct, but you are doing it log n times, right? So your complexity would be actually n log n, not only n.
okay? So in ordinary list it is log n. Here it is n log n. That's it.
Yeah. Because every time you are traveling, and then again you are calling recursively, and that recursion call can happen total of log n time, correct? Because see, by 2 you are anyway doing. Every time you are getting your by 2 thing is anyway happening. So yeah, because here also I told you are going up to length of array by 2.
Yeah.
So if you are doing that, then you would require log n steps to actually find the element. And in each of those steps, you are using the mid, which takes order n time to reach. So log n steps, and each step requires order n time. So that gives you n log n time.
Okay.
Okay. Fine. So that is binary search. By the way, let me ask one more question. So let's say you have an array like this. And let's say 1, 5, 6, 7. Let's say these are 2 arrays. Fine. And the question is, you have to find the number of times, right? The number of times and let's say these are sorted array. As you see that I have already drawn over here, these are the sorted array. So the arrays are sorted, that is given to you. So whenever it is given arrays are sorted, you know that there should be some concept of binary search. So that's a hint. So this is the question is, you have to find number of times a given element. So let's say I give you the element 32 or let's say 64 in the first array, right? I ask you to find the number of the frequency of the number 32. or let's say the frequency of the number 100. Likewise, in the second array, I can ask you the frequency of the number, let's say 4 is 2 times. Let's say 7 is 2 times also. Let's say 1 is 1 time. So I ask you the what is the frequency of the number 3 or 6 or 7 or anything, right? So how can you do it, and what should be the time required for that? But what should be the basic approach? You just have to count the frequency of a number that I give you. How will you do it basically?
First, search for the number and then forward or backward check until it is changing.
Okay, so how much time would that take you? So
Again,
let's say,
log n and some.
is it login? So
Constant.
let's say I ask you the frequency of the number 8, right? I ask you, what you have to find is how many times 8 is occurring in the second array. So you have to search the number. You said that you would search the number. So if you do search the number, you apply binary search, right? At first,
Yeah.
if you do binary
Yes.
search, so let's say that would take you login time. Fine. And then you would go either in the left side or right side, wherever you are, till the
Number
number
changes.
changes, correct. So if I give you an example like this, what would happen? Right? You search the number, let's say the first hit happens over here, correct? And if you apply binary search actually, then the first hit will happen in the middle, right? So you check the first hit and you see, okay, great. Now obviously I'm in the middle of the number 8. Now I have to check on the left hand side and right hand side how many 8s are there till I get a separate number on both sides. So you go on and you see that you have reached the end of the array on both sides. So this is actually taking you order n time because this is your input size, right? So in this case, it would take you order n time. Getting the point? You search the number in log n time only. Here also, let us see in this example, you searched over here in log n time, but here 8 is occurring only once. So that is fine. You will check one comparison on the left hand side. You would say that, okay, that's it. So it takes you log n time in this example. So this is your best case, right? This is your best case.
How do we find the number of, for example, in the second array, if you're having continuous 8, like some, instead of new array, how do we proceed? I'm not getting that code-wise.
Okay, so but
Because we
first
found
of all,
element by binary search. Next step, how do we count? I'm not still getting.
correct, that's what I'm asking. So how do you count? So the first suggestion was that if I need to find the frequency of a given element, that's the question, and my array is sorted, first step is I would find the element itself, right? So if the array is sorted, then I can guarantee that the element would be consecutive, right? The repeated element. It would not be 4 cannot come in between because it is sorted array. So if it is a continuous, sorted array, so and the repetitions are continuous, so wherever I would see that my key is getting matched, that is, I have found the element whose frequency I have been asked to find, right? So let's say 8 in this case, so, and this is the middle one. So binary search would hit this one first, right? This 8, and I get an 8 is equal to the number that I have given you to find, right? After that, what you do is you see, okay, since this is sorted, my repetition would be consecutive. So you just go on both sides and see that at which point the number changes, and you count one by one. So you go over here, add count +1, count +1, count +1. Accordingly, you go over here also, count +1, count +1, count +1. And then you see that array itself has ended, right? So if I take this example, you start with 3, right? You go on the right hand side, count +1, and then you go and see that it is 4, which is not equal to 3, so you do not count this one. And you go on the left hand side again. So +1, +1, you see that this is 2, which is not equal to 3, so stop. So +1 did over here, we did +1 over here, and +1 over here. So, right, and this is the number. So we get the count that 3 is there 4 times in there. But the problem with this approach is, I am saying that if I have an array like this, like all the things are repeated, there is only one element whose frequency I have given you to find, then what is happening? Then you are actually traversing till the end on both sides, right? So this is actually nothing but order n time. So you are traversing the whole array again. So using binary search did not give you any advantage. Okay. I would not tell the answer to this question. Just think about how to do that. If you think, then I mean, you would be a little more advantageous in upcoming examination. Not maybe in quiz 1, but maybe in some other quiz also. But just try to think what it is. How you can do that. Fine. Okay, the problem statement is clear, right? What we need to do.
So basically, we used a binary search only for the first time that we want to find the element. After that, it's just about going one step ahead on both the sides.
Yeah, but that takes you order and time. My claim is you
right.
can do it in order, log, and time.
Yeah.
This is my claim. How to do that, I'm not telling. That's your work to think about, right? So how to do that? Yeah. Just try to do obviously binary search only, but how you can do that? There would be. Let me give you one more hint. So whenever we are checking this condition, right, a mid equal to key, the point where we got the element, you have to actually add one more condition over here. Just and one condition. So yeah, try to think how you can do it. A little more hint if I give that, try to find the boundary where the number changes using binary search itself. Right now, I think that should be very easy. Now, you have to find the boundary where the number changes. I have asked you to find 8, right? Or let's say this, if I take this example, I have asked you to find the frequency of 3. So you find a 3. I mean, you find a number which is not only 3. What you are doing in the first case, you are trying to find where 3 has occurred using binary search. I am asking you, don't do that. What you do is find the 3, but the 3 which is the leftmost 3 and the 3 which is the rightmost 3. Try to find those 2 3s. Once you get that, obviously you know the array index, right? And it is a sorted array. So simply subtracting between them gives you the frequency. So the index of this is, let's say, 0, 1, 2, 3, 4, 5. And the index of this one is 2. Right? So 5, if I do 5 minus 2 plus 1. Right? Plus 1 because it has that element, right? So you get 4. So simply subtracting the index gives you, only thing is you have to find this 3 and this 3. Accordingly, in this example, you have to find this 8 and this 8, right? So obviously this a mid equal to key was the condition when you are finding, right? When the equality holds. But I am asking you, along with this, you have to just add. That's why I wrote you have to put an AND condition which checks that it is the last, I mean, it is the leftmost element and it is the rightmost element. If you can do that, you return the mid like everything same, right? And there would be 2 mids, one for the left element, one for the right element. You subtract those 2 mids, you get the number of frequency. I mean, the frequency of the number. Fine. So now I think I've said first a little bit fill in the gaps. You have to do that. How to do? Fine. So that was binary search. Okay. Any other doubt? No doubt in graphs. I thought there should be more doubt in graphs. So actually for week 6, I would try to discuss as much as possible. But after that, in the next week, actually, we would go in more details of week 6. So before you, so all you have quiz. So that's why I thought that let us discuss if you have any other doubts. And if there are no doubts, then I would move to week 6 now. No doubt in graphs. Great. What is the time complexity for topological sort? By the way, anyone remembers? Okay, fine. Anyways, revise those things. Revise the graphs part very nicely. Right? Fine. So let us start week 6 then. Can someone give me a summary? What was the, I mean, how did we end in week 5? What was the point we last discussed in week 5? Okay, let me just ask this. So can someone tell me what is the running time of Dijkstra algorithm, Prim's algorithm, Kruskal's algorithm, all these 3 algorithms that we discussed? That was the major part of your last week, week 5, right? So what was the running time of all these algorithms? I know you are busy with the quiz, but let's discuss it.
One of them was n cube, right?
Which one?
One of them was n cube.
One of them. Okay, nice. Okay. So let's see. What happens is, so if I take Dijkstra algorithm,
Dijkstra is n square.
Dijkstra, if we take, correct, it is your order of v square, right? And prims is also order of v square. Okay. Now Bellman-Ford and Floyd-Warshall, I'm not going into that. Bellman-Ford or Floyd-Warshall algorithms, those would take you. Bellman-Ford can actually go up to order of cube, I mean v cube time. Why? Because n-1 times you are in Bellman-Ford. What do? In Bellman-Ford, you run the thing for n-1 times, and one more time if you want to check negative weighted cycle n times, right? n-1 times you would do what? n-1 multiplied by all edges. All edges you check the condition, right? Whether your d of u is lesser than, sorry, not lesser, greater than d of u plus uv. And if it is so, then you change d of u equal to this thing. Right? So you apply this condition for all the edges. Now this thing is order 1 time work. This is your order 1 time work, constant work. But you do that for all the edges. So that is your order e time. Or yeah, so here I think the convention is m, so order m time. So the final result is then n-1 into order m, or if I just write it in the whole thing, that order of m into n. So this is your Bellman-Ford algorithm. Now, if it is a complete graph, right, then the number of edges is actually what? It would be in terms of n square, right? N square minus n by 2, exactly. If I go, it's a complete graph. So in a complete graph, I would have edges between every 2 points. So if I have n points, I would get NC2 edges. So NC2 edges is nothing but n square minus n by 2. So basically, this is order of n square. So order of m into n is nothing but order of n square into n in case of complete graph. So Bellman-Ford can range up to order n cube time. So Bellman-Ford was order n cube, Dijkstra was order of v square, n means, okay, so let me just write a naught over here also, n square, right? Both of them would take order n square time. So the whole point of week 6 is Kruskals also, right? Right? What was the time complexity of Kruskal, by the way? So what you were doing is, at first you would sort all the edges. Kruskal was working like you would sort all the edges, and that sorting would take you order of n log n time. We know that sorting takes n log n time. So n log n time would be going into the sorting thing. But the problem is, you pick all the edges one by one, and you pick the minimum one. I mean, pick the minimum every time, right? So that would, at the end, you are doing for all the edges, and you are checking the array to find the minimum, right? So that would again give you n squared time. So all these algorithms were actually running for order n squared time, right? You can just revise the lectures, the live sessions of the previous week. Yeah. So this week, the motive is, see, I think I mentioned this in the introductory session of this course. So whenever you want to improve the performance of an algorithm, or let's say, I mean, you improve the approach of solving a problem, there are 2 ways to that you can go for. First is you totally change the algorithm itself, right? But that is not very easy all the time, because I mean, you think of an approach, you proceed with it, but coming up with a totally separate approach which would take much lesser time is something which is difficult. The second approach is you change the data structure, right? So 2 things: either you change the idea or intuition of solving the problem, which is nothing but your algorithm, or you change the data structure which you are using in order to solve that problem. Now, in all of these cases, what was one common operation that we were doing? So in Dijkstra, we were trying to find the minimum current distance vertex, right? Remember that we had one minimum on a list, right? So we would pick the minimum vertex v equal to minimum of the vertex. So if I go to the Dijkstra, anyway, so we were actually finding the minimum from a list of vertices in Dijkstra, and then we were relaxing. I mean, we are checking this, we are applying this operation on the edges which are incident on that vertex. Right? In prims also, we are doing the same. we were finding the minimum vertex, one minimum vertex, right? And then we were getting who are the neighbor of which edges are the neighbor of this vertex and adding accordingly. In Kruskal also we were finding the minimum, but Kruskal is a little bit different. But Dijkstra and Prims, they are exactly the same code, and we are actually finding minimum in both the cases. And this minimum finding was actually increasing your time complexity. So if I go to the code over here, week by Dijkstra. So this is what I was saying. You see this min, right? So what were we doing initially? This part is the initialization part. We are not doing anything else. From this for loop, the main thing starts. I mean, your for you in range. So for all the vertices you are doing, what are you doing? You're finding the minimum from a list, which is basically your distance v, right? Which is your current distance of each vertex. Now you initialized it with 0. Sorry, you initialized with the infinity value. And one vertex, which is your source vertex, you initialize that with 0, because that would be the first one which would be picked up by this min function, right? Because it is 0. So after that, if it is not visited, right? I mean, if your heap not visited, then you are picking the minimum vertex and storing it over there. And then you are going for all the vertices which are there. You are traversing all the edges and all those things. I'm not going into the detail, but you are picking this minimum. And you see that this minimum finding from a list, right? What is the time to find a minimum? I mean, minimum or maximum element from a list. It takes order n time. And you are doing that for all the, I mean, for u times, right? U is your number of your edges. Sorry, number of your vertices. So this for you, and this finding this minimum itself was taking order n time, and order n into this order n, right? This is also n times. For loop goes till the number of vertices. So n into n squared time was coming, right? So this was actually causing you order n squared time. And we somehow now plan to actually reduce this minimum finding. This minimum finding, we are doing the minimum finding in order n time. If I can reduce it to something more, I mean, in a lesser time, right? Reduce it to some better time complexity, then my order n square can be actually reduced. The whole time complexity can be reduced. How to do that? For that, we use a separate data structure. Here we are using simple list with the distance values. Okay, but now we just need to apply another data structure over here that would find the minimum in a much lesser time. That's the whole idea. Okay, now what is that data structure? So this data structure is what we call the heap, right? And what is heap? The definition of heap is it's an almost, or let's say mostly complete binary tree. Now there are actually multiple kinds of heap. When I write binary, almost complete binary tree, here we are dealing with only one kind of heap, right, in our course, and those heaps are called as binary heap. But since we are not going into other kinds of heap, so whenever we write heap, that means the binary heap, and that means it's an almost complete binary tree. Now what do we mean by almost complete? I would get to that, but basic idea is heap is just like every heap, the heap that we are discussing in this course, that would have only two children. Now what is this children and tree and all those things? I'm coming to that. So what do we mean by that is, so tree you all know, because basic idea is there. What is a tree? And binary tree is such a tree in which every node can have at most two children, right? It can have 0 children, it can have 1 children, or it can have at most 2 children. That's what we call a binary tree. Now what is the meaning of complete? Complete means that at all my levels, the number of nodes would be fulfilled. Right? So this is a complete binary tree. Right? So all the nodes are fulfilled at each level. Right? So this is 2 to the power 0, 2 to the power 1, 2 to the power 2. So dot dot dot, at any point it is 2 to the power of h. So this is a complete binary tree. When we say almost complete binary tree, that means that everything is fulfilled except the last level. So let's say, right? Let's say this is a almost complete binary tree. Almost complete. Only the last level, right? If I say that you do not have this node over here, then I cannot say it's an almost complete binary tree. Right? So only the last level, right? Only this last level, they might not be there. So let's say I take another simple example. This is also an almost complete binary tree because up till this level it is filled. Only the last level has empty nodes, I mean empty positions. So a heap is an almost complete binary tree. And the property of heap is, now let us come to the main property of heap. The property of heap is, there can be two kinds of heap. The first is a min heap. Okay, and I can also have max heap. Now, min heap means the parent node, at each and every parent node must be having a value which is lesser than both of its child nodes. So let's see if I have 32 as this node, right? So I can have these two nodes as some value which is lesser than 32. So I have, let's say 10 and I have, let's say 31. One important point though is that I don't care about the order of these two siblings, right? I can just swap it also. I can just write it 31 and 10 accordingly, no problem. Okay. So I don't care about the order of the siblings. I only care about the relation between the parent and the child, right? So in a heap, there is no relation within the siblings. All the relation is like this in top to bottom manner, that is between the parent and the child nodes. And that relation is in a min heap, parent node should be smaller than all the child node. And in a max heap, parent node should be larger than the child nodes. Okay. So, oh, sorry, I wrote this wrong. It's a 25. Not 25, also 10, right? So I have to put some value which is lesser than 10. So let's say 9. Fine. So this is the idea. In a min heap, the parent must always be smaller than its two children. And max heap, the parent must always be larger than its two children. And accordingly, if I extend this thing, okay, since there is a min heap, so 31 is smaller. So I can put any value which is larger than 31. So let's say I put 65, 41. Here 10 is the smaller value, any value which is larger than 10. So let's say I put 100 and let's say I put 200. Fine. So this is a heap. Acha, by the way, is this a heap? If I write like this, right, let's say 200 over here. See, this follows the parent-child relationship, but this does not follow the almost complete binary tree property because I do not have a node over here at this point, right? So that's why this is not a heap. So heap is almost complete binary tree in which the parent and child constraints hold. Okay, so that is the basic definition of the data structure. Now we would go to some operations of heap. I would be a bit faster over here because we have to discuss at least till the end of heap. And then in the next week, we would have one more session for week 6 because most of you would not be quite okay with the week 6 content now because of quiz. So we would take one more session for week 6 in the next week after your quiz. Fine. So that was the basic heap structure. Now, what was our motivation to learn about heap? The motivation was it would give us a better time complexity to find the minimum number, okay, or maximum number. If you can find the min, you can also find the max. That's why you can use the min heap and max heap, right? So min heap, you learned that the node which is the parent node, it would always be the lesser node than its child. So the node which is the root node, that is the parent of all the nodes, right? So that node must be the smallest node in a min heap. And accordingly, that node should be the largest in the max heap. So you can get the idea. All you have to do is somehow to take this minimum node, which is under this root node from the heap, and you get the minimum value. Now, how to take that out and all those things, now we won't discuss. But before that, how can you make a heap? That is the first question. That we understood diagrammatically that how a heap looks, but in programming, how you can make a heap. So the most preferred implementation is we use a array. Use array as a heap. Fine. Now, what do I mean by that? So let's say I draw a heap at first on the left hand side, and this would be a min heap. So I write 1. Let's say 13. Okay. So this is the min heap. You can see that all the parents are smaller than its children. Now this is the diagrammatic representation. Now how to represent it in array? Now that is very simple. What you do is, let's say this is my array, right? You put 1, 2, 30 consecutively. You do a level order traversal. I would come, what do I mean by level order traversal and all? But basically, intuitively you can understand, right? Level by level you are proceeding. 1, then in this level you have 230, then in this level you have 41, 56, so likewise. 41, 56, 74, 35, and 101. Right? So this is the heap representation. Now you see this is quite trivial. I mean, very normal kind of thing, right? We did not do anything fancy. But this actually gives you a very good property. You can observe that this linear representation of the heap actually has the property to present you the tree kind of structure. Now, what is that property? The property is you take any node, right? Let's say I take this 30. Okay, you take any node. What is the index of that node? This 0, 1, 2, 3, 4, 5, 6, 7. Right? So you take this 30 node, right? The index is 2, right? So what you do is, whatever the index is for 30, this is for 30. The index is 2, right? So you multiply that with a 2 and add 1. Accordingly, you multiply with 2 and add 2. Okay. So these two indices that you are getting, this is the left child of 30 and this is your right child. So you see, just by applying this simple observation, if I generalize this thing, so what it becomes is 2 into root node index, right, plus 1, 2 into root node index plus 2. So this is your left child and this is your right child. So you are getting this tree kind of feature, right, left and right child, just by applying this. I mean, you can see that. So what is this, by the way? 2 2s are 4 plus 1 5. So you go to the fifth index, which is this one. So 74 is the element, and here it is 2 2s are 4 plus 2 is 6. Sixth index is 35. So 30 was our first, I mean, the parent, and we got 74 and 35 are the left and right child. You verify it with the heap, you get this. See, 30 is the parent, 74 and 35 are our left and right child. Fine. So this is how you represent a heap while doing the program in the form of an array. Okay. Now let's come to how you. So this was basically how you represent that. But if I ask you that, I mean, here if we give you an array, right? So this is we just drew the heap. I mean, diagrammatically, and I represented it in this fashion, right? This is the heap representation. But let's say you are given a random data sequence. So let's say, let's take the previous one only, right? 1 to 30, 41, right? Let's say 30, 2, 1, 41, 35, 101, 56, 74. Let's say 74 is over there. So there is a random sequence. Right? So you have been given this random sequence of number, and now you have to convert it into a heap. So this is your basically the first operation on heap, and how you can make a heap. Right? Now I would just go back to the structure once again. So you see, in order to make the heap, right, you have to write some coding you have to do. How you can make this array in the form of a heap? That is basically you can transform this array into this array. Right? How you can do that? So that we would see now. So see, observe it. So if I just put the index over here, 0, 1, 2, see, this is the array index right over here, right? So I'm just adding the index 0, 1, 2, 3, 4, 5, 6, 7. Now, one observation that you have to do, one observation that you do over here is that you find the first parent node from the bottom part. I mean, from the bottom, from towards the leaf. You actually try to find which particular node is the first parent node, right? So you see that this is a leaf node, and we do not have a children node for 101. This is also a leaf node. 35 does not have a child. Accordingly, 74 and 56 also do not have a child. But 41 has a child, right? 101 is a child of 41. So 41 is the first parent node, right? If I even draw another heap, right? So let's say any structure. I'm not putting the values. Let's say this is my structure. It is also a heap, almost complete binary tree. So if I put the indices 0, 1, 2, 3, 4, right? So this node, which is the first, non-leaf node or the first parent node from the bottom, this node, right? 1. Okay. So if I just add one more index, let's say over here, this is 5. So then what would happen? Then this node actually becomes my first parent node from the bottom, because 5, 4, 3 will leave, 2 is the first parent node. Now, the observation that you need to do is that if you do n by 2, right? If you actually find, we have to do some -1 + 1 adjustment over here. Let me just check. So if you do this n by 2 - 1, what are you getting? N is the number of nodes, right? So I have 7 nodes over here. Okay. So this would actually, and if I go like this, so 7 by 2 is 3.5, not 7, sorry, 8. No. So 8 by 2 is 4 - 1, 3. What is this? 4, right? 8. What is the number of nodes in the heap? N equal to 8, correct? Because in this heap we have 8 nodes. So if I have 8 nodes, N equal to 8, so 8 by 2 is 4 - 1, which is equal to 3. Correct? So if I check the index over here, 0, 1, 2, 3. You see, this was our first parent node. Fine. Let me just check it for any other node as well. This -1 thing, I have to check once. Okay, let me check over here. So this is 6 nodes, right? So if I put 6 by 2, which is 3 - 1, 2. 2, correct, yeah. So fine. So if you just use this formula, if you just see this formula, you see that n by 2 ceiling -1 actually gives you the first parent node or non-leaf node from the bottom, right? And why this is happening, by the way? Right? This is happening because our heap is an almost complete binary tree, the main property that we discussed. And that's why you are getting this n by 2. Why n by 2 factor? We would come to these things in much more detail when we discuss about trees. These are not quite required now, but since heap is already a tree, right? So I'm just mentioning this fact. So in a tree, right, if it is a balanced tree, mostly balanced tree, or mostly complete tree, right? In that, what is balanced tree, what is complete tree, all these things we would come. Don't worry. Just for the sake of mentioning, I'm telling this, that this n by 2 - 1 is actually intuitively happening. The reason for that is in a complete or complete tree, like we discussed over here, in a complete tree where most of the levels are filled up, only the last level might not have been filled up. Okay, in such a tree, or even in a fully complete tree, the number of nodes which are there in the leaf, right, that would be equal to the number of nodes which are there in the other part. I mean, so if I just draw this, the number of nodes which are in the middle. So if I have a tree like this, which is mostly complete, you just draw a mostly complete tree and check this. Okay, so how many nodes do I have in the last level? You see 1, 2, 3, 4, 5, 6, 7, 8, right? So that would, here we would have 7 nodes, 4, 5, 6, and 1, 7. So the number of leaf nodes, right, would be always equal to the number of non-leaf nodes plus 1 in a complete binary tree, right? So you see that that's why this factor of 2 is coming. Okay, because it is equal. This the amount of nodes, internal nodes, is equal to the number of leaf node. Okay, so if I want to find the first internal node, I can get that from bottom n by 2 minus 1, because n by 2 would be my leaf node. If n are the total nodes, right, and then I can get that around n by 2 nodes would be non-leaf node and n by 2 nodes would be leaf node in case of a almost complete binary tree or a complete binary tree. Fine. So if n is the total number of node, n by 2, around n by 2, not n by 2 exactly, it would be n by 2 minus 1, but anyways, around n by 2 would be our internal node and around n by 2 would be our leaf node. That's why you are getting this as the this expression is giving you the first non-leaf node from bottom. Okay. So okay, so why are we actually bothered about this first non-leaf node? See, now what we would do is, as of now, just keep this thing in mind. This is important, finding the first non-leaf node from the bottom. Now let us discuss one more property and then we would come back to the making of a heap. Right? So we are just pausing a little bit over here. We were discussing, what were we discussing? We were discussing making a heap, right? Making a heap. So we would take a break from that a little bit. And we would return back after some time. But before that, we would discuss another operation. And that operation is called as heapify. Okay. Okay, heapify. And so what is the idea? So let us draw the heap that we had initially. One, 2, 30, 31, 36. 1, 2. So this was our heap, right? Our minimum heap, the minimum element is on the root. Now, let's say I ask you that what happens is you have to somehow remove the number 30. Okay, you want to remove the number 30 from this whatever, this heap, right? Deleting 30 from the heap. Okay, or let's say not 30. Let's say we discuss the extract min first. That would be actually easier. So the main motivation for coming into heap was we wanted to actually get the minimum element in a lesser time, right? So we see that the minimum element would be the root element, correct? So our plan is to take this root element out. So what would be the time required for taking that root element out? We would come to that, but let's do that at first. Let's say I take this minimum element out. So that operation, taking out the minimum element, is what we call the extract min operation. Okay, extract min operation. That you are extracting the minimum element. Now, if I have extracted this node out, right, I have extracted this node outside. So there is no element over here as of now, right? I got the minimum element 1, but our main motivation was in how much time do I get that? Is it lesser than order n? We would discuss that. But as of now, just think we have taken that out. Okay. So once we have taken that out, obviously this my heap property is lost. This is no more a tree itself. We have to actually make it again a heap, right? Because here we have an empty space. So how to do that? Whenever you are extracting the minimum element, you are taking it out. The next step that you do is after extracting, you take the last element of the heap. At current time, whatever is the last element of the heap, you take that and you place it in the place of the root node or the minimum element which you just took out. So now I say my last element is 101 in this heap. If 101 wouldn't have been here, so I would have taken 35 as my last element, right? So the last element is 101 over here. So what I would do is I would just replace this 101 and put it over here. Okay. You would replace 101 and put it over here. How can you do that? Remember all the steps that we discussed by drawing this tree kind of structure, right? Just try to tally that with how you would do it in the coding part. How would you do it? Since we discussed that this is the last element, right? So last element, how can you get it? You can get it by simply using some size variable, right? Size -1 would give you the last element. So what do? You take the first element outside. That was your extract min operation. First element is the minimum element, and that is what your, I mean, if heap is represented in the form of an array, correct? So you can just take the array 0 element. So if I say H is my heap, you take the H0 out, right? You take H0 out, and in place of H0, right? In place of H0, you put H of size -1, which is your last element. So that's why you took this 101 out and put it in the first place. Yeah, Dripto, you want to ask something?
Sir, what if it is a balanced tree? I mean, all the leaf nodes are full.
No problem. That's what I said, right? So if I wouldn't have 101 over here, I would have taken 35 as mine. The last node is something that matters, size -1.
Okay.
Okay. So take the last node. That's the whole point. So if it would have been a full tree like this, right? And if I remove this element, the extract min has been done, and this is blank now. So which element I would take? This element. This element would be removed and placed over there. Okay. Fine. Okay. So now we have placed 101. But you remember this is our min heap. This heap is our min heap. So that means every parent node must be smaller than the child node. But what we have done is we have taken the last node, and what we can always guarantee in a heap is the last level of nodes in a min heap would be the largest of the elements, right? Because we follow the structure that the parent nodes are smaller. If parent node are smaller, consecutive parents are getting smaller and smaller and smaller till the root, which is the minimum one. Accordingly, we can say, I mean, conversely, we can say that when we go towards the bottom of the heap, at the last level, whatever elements are there, those elements are the largest of the element in a min heap. In a min heap, those elements are the largest of the element. But by the way, can I say those elements are the sorted? I mean, those elements are sorted as well as they are the largest ones? No. If you see this level, this is not sorted. 41 is there, 56 is there, right? 74 is there, and then again 35 is there. But what I can always guarantee is, right, when 101 was not here, right? So assume 101, I have placed it. I have not worked after that anything. But if you consider only this part of the heap, right, you see that these 4 elements are the largest of the elements. So always you can guarantee in a heap, if you have to find the largest elements, you can only search the leaf nodes. All the leaf nodes in a min heap would be would contain the largest element. Accordingly, the minimum in a max heap, the leaf nodes in a max heap would always contain the minimum elements. Fine. So now let's come back to the discussion. So what we have done is we have done the extract min, taken out the minimum element, and then in order to restore the property of heap, because it's not a heap anymore, right? 101 is a larger value than 2 and 30. It's a min heap, so 101 should be smaller than 2 and 30. So in order to restore the heap property, we apply a technique which we call heapify. The name suggests we are making it into a heap, and that's why we call it heapify. Okay, so how we can do that? So what we will do is, you would take the node, the root node, which you have. I mean, first step is you take the last node and put it in place of the root node. This step. Right. Next step is you compare the node, which is this root node, right? You compare the root node with the children nodes and see which children is, so you see that which children is the smallest. Why? Because you consider only this part, right? This part is no more a heap. The whole thing is no more a heap, but I'm going step by step. So this is the immediate part that I'm concerned about, and this is not a heap. Correct? And since this is not a heap, I have to find some substitute for 101, which can serve, which can make this thing into a heap. Now the idea of heap is parent should be the parent should be smaller than children. So what I would do is I would find the smallest element between these three nodes and I would put that as the parent. Okay. So how can I do that? By doing two simple comparisons. I would compare 101 with 2. I would compare 101 with 30. And I would see that which is the smallest of all of them. So I can see over here 2 is the smallest of all of them. So I place 2 in place of 101 and 101 in place of 2. So what will my heap become? 2, 101, 30. Rest of it remains same as of now, 41, 56, 74, and 35. Okay. So we have done till over here, right? This is the part that we have worked. So you see that this part is a heap. You agree? Right? This is a heap, right? Smaller value.
Right.
Good. But the problem is now that although we got this part as a heap, but this is no more a heap. Initially also it was not a heap, I think. No, initially it was a heap actually. 240 and 56 was serving as a heap. But since I made this swapping, right? So I destroyed the heap property of the left subtree of 2. 101 is a larger value than 41 and 56. So again I do the same step. Okay. Again I do the exactly same step which I did. I would compare 101 with 40, whatever it is, 41 and 56, find the minimum and place it. So 2 would be here and minimum is 41. Swap 101 with 41. Put 56 over here. 30. 74. I don't disturb anything which is not which is not swapped, right? I keep it as it is. Now you see, now this is a heap. 2 is the minimum value, right? 41 and 30 are both larger than 2. If I consider this part, 41 is smaller than both 101 and 56. 30 is smaller than both 74 and 35. So this is a proper heap. Right? So I got a heap. So it's very simple operation heapify. What we do is we consider the root node, we compare it with both of its child, we find out the minimum one, swap it with the parent if it is the minimum, and then again repeat the step for the swap node, right? So if I have to write a little small code for this, how would that code look? Right? Let's say I call the heapify algorithm. Okay, whatever the elements are. Obviously, basically this would be the heap, nothing more. Right. First would be the heap itself, which is an array, by the way. Array list, whatever. In Python, when you code, you would make it as a list. Okay, so heap and then one index. Now I am writing this as the root because we start the heapify work from the root, right? So root. Now what are the steps that I would do? Okay. First thing is we need to do two comparisons, right? So just write it as it is, heap h of root if that is let's say larger than my Okay, now larger than what we were doing is left child and right child, right? Now I discussed that left child was what? In the array, left child was 2 into the index of the root node plus 1. And right child was 2 into the index of the root node plus 2. So I'm checking for left child at first. So 2 into root. Okay, 2 into root plus 1. So if h root is, oh sorry, not 2 into root. H of 2 into root plus 1. Fine. So I see this element is the smaller element. The left child is a smaller element. Okay. Actually, there is one more condition over here, and that condition is what? I would come to that a little bit later. Okay. But with the algorithm, it doesn't matter. I mean, just the algorithm is same. This condition is basically a boundary condition. I would come to that after discussing the whole thing. So first thing is we compare, we find this thing. If it is lesser, then I would write there is a, let's say, a smallest variable. I initialize the smallest variable with, let's say, this value, right? Whatever it is, this 2 into root plus 1. The left child index, right? Which is the smaller. And then what I do? Again, I make the second comparison. I have to find the minimum among all of them, right? So if this is the case, then smallest equal to 2 into root plus 1. And here initially, let's say I made smallest equal to root, right? So I am starting the work with assuming that root is the smallest element. Okay. And then I check if left child is smaller. So I initialize smallest with 2 into root plus 1, which is the left child. And if that is the case, what I would do is I would check h of smallest. Okay, h of smallest. If that is larger than h of 2 into root plus 2. Now, what does this mean? This is my right child. So at this point, the smallest value that I got, whether it is the root itself or whether it is the left child of the root, that would be present in the smallest variable. Right? If this if case does not satisfy, then obviously smallest would be the root. So I would compare that, and if I see that the one condition, I would come to that later. If I see that the right child is smaller than the all the other two nodes, right? So I would again modify smallest equal to 2 into root plus 2. Okay. So at this point, whatever smallest would store, that would be the least number. After that, what we do is we check remember what we did? We made a swap, right? We would do a swap with the smallest element and the root. But what happens if the root is itself the smallest? In some scenario, it might happen, right? The root is itself the smallest. Actually, both this if case actually resulted in false, right? So that's why we make also again a check over here. If my smallest is not equal to root, right? So that means it's a valid case. That means root is a larger number and my heap property is violated. So I must, there is some other, the children node are actually smaller, right? So what I would do in this case, I would swap smallest and the root.
So could you repeat this again? Sorry, I missed this actually. The if smallest not equal to root.
Okay. So let's say in this tree, what would happen? This tree 41, 101, 56. Assume this is the root. Okay. What would happen? So you see that 41, you do the comparison, first comparison with the left child over here, right? What is the left? This is left child comparison. So this is your left child comparison. This is your right child comparison. So you do the left child comparison, the first if statement, you see 41 lesser than 101. You see, yeah, okay, 41 is lesser than 101. So that means the root node is lesser than 101. So what would smallest, I mean, this would be a false case, right? If statement couldn't be true, right? So if is not executed, so at this point, smallest is equal to the root only, the initialization. Then again come over here, the second right child comparison. I see that right child is 56 and 41 is my root. So again root is smaller. So again this if statement is also fetching you wrong, right? So again smallest is not executed. I mean this line is not executed. So both of these ifs went false, and that's why the initialization of the smallest variable is the current smallest number, and that is itself the root, right? And which is correct because in this tree I have 41. The root itself as the smaller node. I do not have to worry about. I mean, it is not disrupting the heap property. So we have to take care of such situations also, right? So in that kind of situation, I must not swap because already the root is itself the smallest one. I would swap whenever one of the child is the smaller, and then I would take the smallest child and place it in place of the root. Sorry. Right? So that's why we do this. If smallest is not equal to root, that means if smallest is some child, it can be the left child, it can be the right child. If it is that one of the child, then I would swap. If it is root, I do not need to swap. That if it is root, that already means that my heap property is satisfied. And that's why my root is the smallest one. So no problem. So here I go. If smallest not equal to root, then I do a swap, right? And swap method would what it would do? It would swap the value of each root with each smallest. Okay. And finally, what did we do after that? We did the swapping, and remember in the first step what happened? Over here. In this tree, we made a swap, right? We put 101 in place of 2 over here. But as soon as we do that, we saw that 101 was disrupting the heap property of this part of the subtree, I mean this subtree. So again, we called the same process of finding the minimum on this 3 node, right? So the node on which I am doing the swap, I have to again call the same heapify algorithm on that. So this is a recursion, right? I would do that again. So what you do essentially over here is, after you made the swap, you call the heapify again, but this time the heap obviously the root, and what should I write over here in this place? Can someone tell me what should I write? So on which node are we doing the swap?
2 of root plus 1.
Okay, so 2 of root plus 1 would be in this case, that is correct.
Smallest.
But,
Smallest.
Correct. So we are actually doing that with the smallest one, right? Because I'm swapping the root with the smallest, right? And then I would again call the it on smallest one.
Sir, over here, while we are swapping, shouldn't we swap the indices instead of the values?
Why would you do that? Doesn't matter, right? You can just swap the values. That's what matters. Indices,
then,
how would you swap it? It's an array, right? But so whenever I'm drawing this in the form of a tree, this is an array. This is nothing but your 201, 30, 41, 56, 74, and 35. Now, all I want is you swap 101 and 41, right? Oh, no, sorry, 2 and 101. Oh, no, sorry, 101 and 41. To do the swap. So it just boils down to this. In an array, you want to swap these two numbers. That's it. So why would you swap index? You would simply swap values.
Okay.
Okay.
Also, sir, while comparing the smallest with both the roots, both the children, is it necessary that we compare it with both children? Is not one child enough to compare? I mean, if I compare it with one child, whether it is smaller?
Fine, no problem. Let's check that. What happens? So let's say I have in a heap, I have, let's say, 201 over here. And I have, let's say, 46 over here. Right? And let's say I have 20 over here. So you do the left child comparison at first, right? You do this with 46. You say, okay, fine. 46 is a lesser number. So let me swap 201 and 46 to do that. Is this a heap? I mean, big heap.
It is not, because 20 is bigger, is smaller, sorry.
Correct.
Yeah.
So that's why it's important that you take the smallest of all of.
Okay, sir. Okay. Got it. Thank you, sir.
Okay. So yeah, that's it. This was it. I mean, the EPFI algorithm. Only one thing, that we are doing this recursion, right? We are, I mean, calling this again and again. So if I have these subtrees, right, and I somehow, by making a swap at this level, right, I disrupt the heapiness of this level. So again, I call heapify on this level, and let's say I again have a node over here and make a swap. Let's say this time with this level, I make a swap. This node, right? This node and this node, I make a swap. So again, that disrupts the heap behavior of this tree. So again, on this node, I call heapify. So again, this is again, I mean, this subtree. So basically, we are calling heapify on I mean, each of these subtrees of three nodes and proceeding till the bottom. Now, this recursion is happening till the bottom, but did we write any base case, or did we write any? This is a recursion, so it must have a terminating condition, so where it moves out of the recursive calls, right? So, but can you see any base case or anything over here? No, because there are no base cases. I'm just calling heapify. But how, at what time the algorithm stops? The algorithm stops when you have reached the end of the tree, right? So when you reach the bottom level of the tree. So like here, we actually disturbed this part at first, then disturbing this created a disturbance in this part. So I again change this part, and finally we see that this is a proper heap, and we have reached the end level, right? There are no more levels, and that's why it's a heap. Fine. So when you reach this end, that's the terminating condition. So how can we actually check for that? So we are proceeding with the smallest. What is there in the smallest, right? So when you see I'm putting smallest, right? So when we are putting the smallest in the root, right? So what are we putting? Either the left child is there in the smallest, or the right child is there in the smallest. Okay. So whenever you are comparing the left child and the right child over here, you have to check whether that is within the range of the array itself. Let's say you proceed one by one, and at some point you actually, let's say this is your array and you had only this much nodes, right? And you proceed. So what would be the left child and right child of this node, right? This is the end, right? Or even this node actually. What would be the left child and right child of this node? It is, I mean, you would have no nodes, right? Nothing would be there. So if I do 0, 1, 2, so 2 into 2 plus 1 would be the left child, 2 into 2 plus 1 would be the right child. So this is 5, this is 6. Now you see that here I have only index up to 0, 1, 2, 3, 4. But here I am getting 5 and 6. So this is your terminating condition, that I have already moved out of the array. I have actually, there are no more further leaf nodes, right? So all the, I mean, everything that I have to do over here is 2 into root plus 1 if it is lesser than the size. That's it. Accordingly, 2 into root plus 2 as long as it is lesser than the size. So these are your heapify's terminating conditions. These two conditions are basically your recursion termination. Okay. So that is your heapify algorithm. Fine. Now let's discuss one more thing.
Okay, so also if no swaps are made, that is if the smallest is equal to the root, then that would mean that we have to return the call, right?
Sorry, if that would mean that
if we are not getting into this if block, that if smallest is not equal to root, that is if smallest is equal to root, then we need to return the something.
Yeah. Okay. I mean, we are just returning. Fine. Okay. So that was your heapify algorithm, and also we discussed the extract min, right? So extract min is you taking the first element out, putting the last element in place of the first element, and then you are calling the heapify method to actually reinstate the heap in its normal form. That's the whole process. So we learned about the heapify method. We learned about the extract min. So can you define that how the extract min function would look like by using the heapify method? If I write extract min over here, whatever it is, right? What you would do is you would simply put in some variable, let's say the minimum, right? Minimum equal to your heap's first element, right? And then what you do is you simply put your heap's last element in place of the first element of the heap, right? And again, one more thing that you do is size minus minus, because now you have removed this minimum element, right, out of the array. So you have to reduce the size of the array by 1. And what you have to do after that? You have to call the heapify to restore the heapify. I mean, to restore the heap. On which node? From the starting, that is from the h, 0. Because this 0 is your last node placed, right? So now you will call from the root. So this is basically your extract min method. Okay, so extract min done, heapify done. Now let's come to the main question, for which we came to the heap. How much time does this heapify method takes? Just look at this function over there. What is the time that you think it would take? Just go part by part. How much time does this 2 lines take? A simple if comparison, right? You are not doing any loop or anything. Order 1. What is same thing? Order 1. Same thing, order 1. So everything is order 1 operation. So the whole function is taking order 1 operation, heapify. So that means what? Heapify is order 1?
Recursion.
Correct, recursion. Now how many times? What is the condition for termination? That I have reached the end of the tree. That is I have reached the leaf. From which node I have started? The root node. So that means what? You are starting from the root, you are applying heapify till you reach the leaf node. So how many times you are doing that? You are doing the order of height times. What is the height of a mostly complete binary tree? Log n. Right? Okay, so I don't think you know that. So why log n? By the way, height. This is okay, right? You are getting this idea that since I'm starting from the root and going till the leaf, that's why I understand that I have to do that for the number of, the height, the number of times we have the, the edges on the height, right? So those many times I have to check in worst case scenario. So order of height would be my time, order of h into order of 1, which is basically your order of h. Now, order of h is nothing but order of log n. Now, why it is that? Why you are calling that order of height is actually equal to order of log n? So we told you that heap is a binary tree, right? Almost complete binary tree. So at every level, I have 2 children. First, like this, like this. So every level, I am increasing my nodes by 2, and I'm doubling it up. Correct? So if I'm doubling it up at each and every level, let's say we have total of n nodes, right? Total tree has n nodes, right? If total tree has n nodes, and if I'm doubling it up at each level, so the first level would have what? 2 to the power 0 number of nodes. Second level would have 2 to the power 1 number of nodes, and dot, whatever. Right? So 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus dot plus 2 to the power. Let's say the height is, what is the height of this tree, by the way? 2, right? Number of edges from the root to the leaf node is the height of a tree. So height of a tree is 2 in this case. Okay. So I would go towards the 2 to the power 0 plus 2 to the power 1, 2 to the power of my height h, right, equal to n. Now if you do this summation, not comma, this is plus, sorry. Now if you do this summation, okay, so you would get what it would get. You would get this as 2 to the power of h plus 1 actually. Right? This summation would give you 2 to the power of h plus 1. These are a geometric progression, right? You just apply the geometric progression rule. You would get 2 to the power of h plus 1 equal to n. Now if you take log on both sides, so you would get log n equal to h plus 1 into log 2 base 2. So log n minus 1 equal to the height. So this is exactly the height. But if I just write in terms of order, so it would be order of log. Fine. So this 2 factor is giving us the height as order of log n. So my height would be order of log n, and my all other operation in heapify takes constant time. So the overall time would be order of h into order of 1, that is order of h, that is nothing but order of log n. So heapify is taking you order of log n. And max, what was the extract min? I wrote the extract min method over here, right? Over here. So obviously this is also order 1 operation. This is also order 1 operation. This is also order 1 operation. Only we are calling heapify in this case, and starting from the 0th node or the root node. So we already saw that this takes order of log n time. Heapify takes order of log n time. So how much time does extract min takes? Order of 1 plus order of log n, which is nothing but order of log n. Now see, you got the minimum element in log n time. Right? Initially, when you are doing a search in an array to find the minimum element in Dijkstra, right? When we were doing that, we were getting order of n time. So finding this minimum element is now order of log n time. And remember how was the structure of Dijkstra? You were running for all vertices, V element of G. You were inside this, you had this, let's say vertex, current vertex, right? Equal to minimum of the, here you had this D, I mean this list, right? D, the distance list. You are finding the minimum where visited not equal to 1. So those things were there. So this was taking you order n time, right? This is taking you order n time, and this is also order n time. So you are getting a order n square time thing, right? But now when I use a heap in order to find this minimum, and in case of min, I would write extract min. Extract min from the heap H, right? And put it in the current vertex. So that would give me order of log n time count. Okay, and I do that for how many times? For n times. Same thing, I have not changed anything else, just I have used the extract min function of the heap data structure over here, of the heap. Right? So order of log n time is taken, and n times you are doing that, so the whole time complexity actually boils down to n log. So that is the whole idea of your improvement of Dijkstra's algorithm. And Prim's algorithm also exactly works in the same way. As you have seen that Prim's and Dijkstra, their code are exactly similar. Okay, there is very little difference between the code of Prim's and Dijkstra. So just like we find this statement, right? This exactly copy paste this line is there in Prim's as well. This vertex equal to minimum of the vertices from a list. So in place of like Dijkstra, exactly like that in place of Prim's also, if you remove that and place this extract min, right? So now you get a log n time work. So in both these cases, Prim's and Dijkstra algorithm, by using heap rather than a simple array, we can get this order of log n feature for extracting the minimum element, selecting the minimum node at that point of time. And that's why our whole complexity now boils down to order of E log B or N log n, whatever. I mean, it is E log B actually, because that takes, though that analysis has already been done, right? Because I would do that again, but that is kept for the next day. I think I would do that whole analysis, code analysis in the next day. Again, why it is E log B and not only N log B? Because basically you are doing that for all the edges. I mean, you can check that in Prim's, I'm taking the edges once and putting it into the heap. That part we would discuss in the next day, no problem. I would go through the code line by line and discuss. But let us discuss the heap thing properly at first. So, but idea is this much, okay? The main the main motivation for heap was I want to find an order log n time approach to find the minimum element, and that would actually reduce my time complexity into a n log n time from an n squared time. So this line was actually creating the main difference. Right? So I just mentioned that, but the whole code with the heap I will discuss next day. But before that, let us complete the making a heap part. This part we did not discuss. We said that we are taking a pause. Let us discuss the other things, and I would come back to the making a heap after this. So we have discussed how to reinstate the heap property. We have discussed how to extract the minimum from the heap, but we have not discussed how to make the heap in the first place. Okay, we have not discussed that, so let's do that at first. So now we will discuss how to make the heap. So let me just take a random sequence of numbers. Okay, let's say 4. Fine. So this is a random array that has been given to you and you need to convert it into a heap. So how will you do that? So if I just write this in the form of a tree structure, see what happens. Okay, as it is, I'm not making into heap or anything. I'm just writing it in the form of the tree structure. So what are we discussing now? We are now discussing that how you can make the heap in the first place. I mean, at first, the first step is you have to make the heap, correct? So that we have yet not discussed. So that's what we are discussing. After that, you get heapify. After that, you get extract min and all those things. But at first, you have to make the heap. So this is the array. I mean, we know the equivalence between array and the left and right child, right? 2 into I plus 1, 2 into I plus 2, that whole thing. So obviously this, if I represent in the form of a tree structure, this and these are equivalent. So this is my tree structure. Now, one point we discussed while we started with how to make a heap concept, that is we got the first non-leaf node from the bottom, right? That we discussed, and that would be equal to the n by 2 minus 1. Why? Because in a mostly complete binary tree, around half of the nodes would be internal nodes and half of the nodes would be leaf node. Okay, so if half of them are leaf node, so the first non-leaf node would be n by 2 minus 1. That's the whole idea, because half of them are already leaf. So if I do n by 2, that gives me the first element, which is the the last leaf element. And if I do subtraction by 1, then I get the first non-leaf element. Okay, so I've discussed that. You can revisit that part of the session if you have doubt. But we got n by 2 minus 1 was giving me the first non-leaf. Okay, now see, can I say if I consider only this node, right? Only this node. Is this a heap? Only 22. This is a heap. This is a trivial property, that because what are the properties of a heap? It should be a mostly complete binary tree, right? What does mostly complete binary tree says? That except the last level, all levels should be filled up. So if I have a single node, right, like this is a single node, 22. This is a single node, 44, right? So that means there is only one level like this single node, and obviously 2 to the power 0, which gives you 1. So you have a single node, and that is basically mostly complete binary tree must have one node in the starting level, right? So that's why it is by default it is a mostly complete binary tree. And also we need the heap property that the parent should be smaller in case of a min heap. Okay, in case of max heap, parent should be larger. So okay, we are discussing the whole thing on min heap. So parent should be smaller than the children, right? So I do not have any children over here. So trivially it is satisfied that it is smaller than children. Fine. So 22, 44, 35, all the leaf nodes, they do not have any child, and that's why, because they do not have any child, they do not have to worry about their smaller value than the child. Okay, that constraint they can be, they don't worry about it. Only thing is, when I have a non-leaf node like 31, then I have to think that, okay, I must have the parent as smaller than the children. Fine. So now you see, why we actually tried to find out the first non-leaf node is the fact that we do not need to apply any work on these nodes, right? We would keep the leaf node as it is because they are by default working as a heap, and they're not violating the heaps condition. So the first node on which I do some work would be the 31 node, the first non-leaf node. Okay. Now what do we mean by do some work? The work we have already discussed. Right, and that work is again heapify, because this is not a heap. Whenever you are trying to reinstate the heap property, right, only thing that you have to do is the heapify operation. Right, so heapify you all have understood, then the whole heap thing would be very easy to understand. We are just using the heapify algorithm in a tricky manner in all different other all the other algorithms. Okay, so here also again we use heapify, only this time we would use from 31 at first. Right, so let's see what happens. So if I use heapify on 31, 4 would come in place of 31, right?
Sir, how did we get 31 again?
By I told now the first node which has children, that is the first non-leaf nodes. Okay, nodes are not nodes, node. And how did we get that? We get that by n by 2. Okay, let me check for this.
Okay.
Okay, there might be a little bit change in the end cases, but let me just confirm it. There are 9 nodes, right? So if I do 9 by 2, that would be 4.5, which is 5, minus 1, which is 4. Okay, so that's why I said that there might be some changes.
No, so if you do the double slash operation, probably you'll get it n by 2.
But that is not theoretically the correct expression to
Yeah,
write.
it is the ceiling, basically.
Yeah. So actually, if I do not go for ceiling, then what happens? So 9 by 2, 4.5, 4 minus 1, 3. But again, let's say if I would have, let's say 6.
Then you
Let's
could
say
take a floor, right, sir?
6 by 2 would have been 3 minus 1 equal to 2, right? 3 minus 1, yeah, 2. So 2. So if I would have 6 nodes, that is up to 5. Then 0, 1, 2. Okay, great. Yeah, so this works. You do not have to take any, I mean, yeah, you can take the floor thing actually. That means the normal operation, n by 2 minus 1. Okay. Correct. So you can do that. Fine. Anyway, so you just take care of this thing, but the whole point is that it would be n by 2 minus 1. That's the whole idea, and that's how we are getting it. So okay, let me just go back to this part where we were checking the heap thing. Okay, so we swapped 4 with this 31 was swapped with 4 because 4 is the minimum element. Heapify, same heapify. There is nothing different that we are doing. So 4, 31, 22, we do that. And after that, what we do, right? So here we are only applying it on the first node, like so. So that's the whole idea. So whenever you are making a heap, you are checking the first step is find the first non-leaf node. So which is this node, right? Apply heapify on that. So you applied it. And then again apply heapify on the next non-leaf node. Fine. So what is the next non-leaf node? This is the next non-leaf node, 60. Fine. So again I apply heapify on the next non-leaf node. So by the way, how would the tree look at this point of time? Wait, 4, 22, 31, right? So 2 here and 9 would be here. 2. Fine. So on which node did we apply heapify? The first non-leaf node, which was this one, right? And we made the swaps. Sorry, this was 22, 31, 4. Yeah, fine. Okay. So I applied the heapify on this node actually and made the heapify thing work, right? After that, I would apply heapify on the next non-leaf node, right? Here you are applying on next non-leaf node. In extractment, what you are doing, the one with which you have swapped, right? The one with which you have swapped, that is the smallest index. With that, you are applying heapify. Here you are not doing something like that. Here you are doing heapify on all the consecutive non-leaf nodes. So on 4, it has been done. Now I would apply on 64. Because 64 is the next, the previous one, just before 4, 64 is the next one. So in the array, you would get 64 after 4, right? So you would apply heapify on 64 and see that what happens. So here again, 8 would be swapped. So 8 would come over here and 64 would go down. Fine. Again on the next non-leaf node, which is 2 now. Okay, so on 2 I apply. So I see 2, 4, 9 is satisfied. It's already a min heap. And then finally again next non-leaf node is 12 now, right? So 12 is not satisfying because 12 is lesser than 12 is greater than 2 and 8 both. So I would take the minimum one. So I would place this 2 and 12. But see what happens at this stage. We made a swap, right? The heapify algorithm worked, but now we have called heapify, remember? So when I'm swapping 2 and 12, again 12 is actually disturbing this part of the heap, right? Like the previous term. Like the previous case, like we discussed. So again, I would apply heapify on 12, right? You don't have to call it. That would implicitly be called by the recursion, the heapify itself. So again, 12 would be called for heapify. And then I would see that 4, 9, 4 is the minimum one. So 4 comes over here, 12 comes over there. But then I check again, I might have disturbed the heapify property of this tree. So again, I check 12 with 22 and 31 and I see no, I have not disturbed the property. So it is fine. So my final structure is something like this. This is my final heap. So you see 2, 4, 8, 12, 9, 31, 22, 64, 35. Right? So you see the 22, 31, 12 is lesser, 12 and 9, 4 is lesser, 64, 35, 8 is lesser, 4 and 8, 2 is lesser. So this is a proper billion. So what is the thing that we did? Step 1, find the first non-leaf node. Step 2, apply the heapify algorithm on every subsequent non-leaf node to the root node. So from this node to the root node, you would apply heapify one by one. So first on this one, then on this one, then on this one, then on this one, like that. So this is what your build heap. This algorithm is you're building the heap, right? From the random sequence of array. So this is what we call the build heap algorithm. Okay. So what are the things that we learned? We learned extract min. We learned heapify. We learned build heap. Okay. One more operation, quite simple. That is the insert in a heap. And finally, the fifth is search.
Sir, I have a doubt here in the build heap.
Yeah.
Sir, while building heap, I mean, how do we give the command for stopping it? So like you went up to the root node, but still we saw that 12 was creating a problem. And then we came back again down.
Very good. Yeah. Yeah. The thing is, that thing you do not have to worry about. So if I write the build heap method, let me just write it. It's pseudo code. And now I'm starting to write the build heap method. First, what we would do is we would apply the build heap every time on. Sorry, we would apply the heapify every time on the nodes which are non-root, starting from the the nodes which are non-leaf, starting from the first non-leaf node. First non-leaf node we got. Let's say I equal to the number of element, right? So n by 2 minus 1. Right? This is my, let's say from this I am starting from I equal to this number 2. I would go till 0. Okay, I do not have to worry about if the last 12 again breaks the heap property, what I would do. I do not worry about that. How it is handled, we would discuss, but let's see. So I give the condition up to 0. So you would go till 0 and you would decrease it by minus. That is every time I is reduced by 1. I mean, so basically you're starting from n2 by minus 1 to 0, you are going by every time reducing I by 1. So basically you are calling on all the subsequent nodes. Right? What you would do is simply call heapify. Heapify on h, I. And that's it. This much, only this much is what your build heap does. Now the question is, what happens in the last level when we actually swapped 12 over here? See, we have reached the 0, right? So the last swap of, I think 2 with 12, right? So the last swap of this 2 and 12, okay? So let's say 12 was here and 2 was somewhere over here. So last swap was the last heapify call. So basically what I mean is the last swap when happened, I was equal to what? 0, because we have reached the end, right? So heapify on 0 is what we call, right? And that's your terminating condition. But now you are saying what happens after the swapping if 12 is creating the mess. The thing is, you do not have to worry about that mess, because heapify, remember, itself had that recursive structure. That heapify would be having these lines of code, and at the end it would again call heapify. So this heapify will take care of that 12, because if it destroys the heap property of the left subtree, right, then this heapify would be called on this node actually. So whenever you are calling this heapify in the build heap method, that is only called up to heapify of 0, right? That is called up to heapify of 0 only. So last call inside the build heap methods for loop for heapify method would be till 0 only, right? And if that swap with 0 makes a mess of the heap, right? So that heapify call, this heapify call, right? Heapify 0, this heapify 0 call, h comma 0, right? This again itself, it's a recursive call, because we know inside the body of heapify recursion would happen, right? So the heapify h comma 0 call, when it is called, it would go down, it would make the swaps, and after making the swaps, it sees that I have meshed this node out, right? And the left side node, it was making the disturbance, right? This is the main heap. This is the correct heap. So do not consider 4. I mean, when 12 was there, at that point, right?
Yeah.
So this heapify would actually call on 12 again,
Yeah.
because you would swap 12.
Thank you, sir.
Fine. So okay, so that's done. So now next thing is insert operation. Now insert operation, let me just draw it on this heap only. This is 4. So inserting into heap is quite easy. All you have to do is, again, whatever new element has been given to you, you put that as the last element of the heap. At first do that. So basically in array, what you would do is, you would at first, since you are increasing the size, so you do in size equal to size plus 1. Okay. And then you write h of size minus 1 equal to your new element, whatever the new element that you need to insert. That one. So what does that mean? This basically means that you have put a node over here, because this is the, so you don't have to worry about whether it's a left child or right child, right? That would automatically be taken care of by the arrays 2 into I, that property. 2 into I plus 1 would be left, and 2 into I plus 2 would be left right child. So in graphs, in visual structure, you put it at the last, right? Whatever is the last. So let's see, if my tree would have been like this, right? Like this, then my last element would be like this. If my tree would have been like this, then last element would be like this. If my tree would have been like this, like the one you are seeing right now, then the last element would be like this one. Okay, so anyways, so whichever is your last, whatever is your last slot, in that you put the new element that you want to insert. So give me any number. Can someone just tell me a number? Preferably a smaller one, so that I can get more example to run it. Just tell me any number.
1.
1. Okay, great. So 1. So right. So how would you do that? You first insert the last element. Right. So last is over here now. So insert it. After that, the only thing that you have to check is, the whole idea is it's a min heap, right? So all the smaller numbers should be on the top, and the smallest number is the root element, right? So I have to check whether the currently newly inserted node, whether it belongs to a upper level or not. That means whether it is smaller than its parent or not. Okay. So you compare 1 with 9 and you see that, yeah, it is smaller than its parent, and that's why you make a swap. Fine. Again, you check whether I have reached my proper level, or am I still lesser than the parent node, my new parent node. So you see that 1 and 4, again 1 is much lesser than 4. So again there would be a swap. Just so basically this is insertion is simply you check with the parent and swap whenever you are smaller than the parent. Okay. Again my parent, this time 12 is the parent. Sorry, not 12, 2 I mean. 2 is the parent. So I compare to 1 with 2 and I see that, okay, again I am smaller. So, and you see now I have reached the 0 index. So that would be your termination condition. So since I have reached 0 index, that's my, I am at my proper level. Fine. So either you have reached the 0 index, that means you are the smallest one in the whole heap, or let's say your parent is actually smaller. So if I would have taken a number like, let's say 3, right? So 3 and 4 would have been swapped at this place. but before 2 it would have stopped, right? So 3 would be placed over there. So this is the way you insert. Now if you have to write the code, again very simple code, only one for loop you have to write. The for would start from which node? Obviously you are adding it to the last level, so I would be equal to your size minus 1, whatever, right? And from that you would go to 0, but your increment would be by how much? That's the question. So what are you doing? You're comparing every time by the parent node, right? You're comparing with the parent node. So what would I become? Every time, what is the parent by the way? How can you get the parent? The child is actually 2 into I plus 1 and 2 into I plus 2, right? So if I give you any of the child and ask you who is the parent, how can you find out? You can simply find out by, you can divide it by. So let's say I want you to find the left child, you do left child minus 1 by 2, right? And if I give you the right child index, you do right child minus 2 by 2, right? To get the parent. So, but here I do not have to go for right and left child. I just want to see who is the parent. I don't care about whether I am a right or left child. So in that case, only thing is if you do even by 2, right? Left child or right child, whatever, any given child by 2 gives you parent's index. Just check that. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So I do 9 by 2, which I get as 4.5, but it would be actually 4 because that would be truncated. And anyways, this is actually the floor part. You would take the smaller one. So 4 is the index, right? So you see 4 is the parent of 9, the index 4. Again, let's say 64. So 64 is 5, right? What is 5 by 2? Then 2.5, which is 2. So you see 2, the index 2 position is the parent of 64. Right? In, let's say 35. So 6 by, what would be the your index for parent if you do that? So you do 6 by 2, you get 3, but that minus, again that minus 1 factor is coming, so you have to consider that. There also it's C by 2 minus 1 actually, and you have to take in this case again the floor, right? No, not floor. In this case you have to take the seal. Okay, accordingly. So that seal thing you have to actually worry about. So everything, every time you do C by 2, either seal or floor, and then you go for minus 1. Same step like we did in the previous case to find the first non-linked node. Likewise, you do that. Just be careful about when you take 1 or 2 example while you write it in the paper. Okay, it's not possible to remember whether it is a seal or floor, but when you write it in the paper, I mean, if it is given in the form of an MCQ, then just take 1 or 2 example, you would get whether it's a seal or floor, whether it's a minus 1 or not. It would be C by 2. Okay, this form would be there. So check that. So if I do that, so I would get 3 by 1 minus 2, that gives me 2. So likewise, you can get the parent. So every time I'm modifying I, right? So I would modify I by this factor, right? I equal to I by 2 seal of minus 1. That's it. That gives you the parent. Okay. And then you compare, I mean, just compare whether it is lesser or smaller, and that's it. Fine. So, and how many times you would run it? You would run till you reach 0. So basically this whole step, this is the path in which we travel till the simple thing. Now last thing, that search. Now see, the problem with heap is there is no specific relation between the siblings, right? That we mentioned, that 2 and 8 over here has no specific relation. 12, 4, 64, 35. There is no relation horizontally. All the relation is in the vertical manner. That is parent-child relationship. But there is no greater or less than constraint among the siblings, among the children's, I mean, right? So that's why you cannot, at every level, you cannot understand, I mean, guarantee whether I should move left or right, with which direction I should move. Like in binary search, you had a sorted order, right? So that's why you could decide that I would go left or right. But here you cannot decide to go left or right. Only thing you can decide is I would go bottom or top. If you get a number that is smaller, then you, if your current value is smaller than the key value, right? Then you know that my key value is somewhere at the bottom, towards the bottom, right? So that you can do, but you cannot just actually have any relation on the levels. So, but having this relation or constraint between the parent and child does not help you to search, because searching is specific task, right? It's not like I mean, you have to search a specific number. And if you do not have any relation between the siblings, right? So I cannot say which one would be the, I mean, there is no greaterness or greater or less than property. So all these 4 nodes, I am not sure. I have to check manually these 4 nodes. Only thing I can be sure of that my key value might not be present in the second level and it must be present in the third level. Why? Because my key value is larger than both 2 and 8. So I am sure that it would not be on the top because it's a bin heap. So all the values on the top would be lesser than the children. And if 2 and 8 are actually more than my key value, that means 1 would obviously be more than my key value because 1 is parent of 2 and 8. So only thing you can guarantee is I have to move up or I have to move down. But you cannot guarantee within the level anything. So that's why you have to come to a level and then search for all the elements. Right? And at end, I told you that if there are n elements in a heap, then around n by 2, actually around in order of n by 2, if I write order of n by 2 element would be internal nodes and order of n by 2 element would be leaf nodes. Right? Which is basically order n. In both cases, it is actually order n. So if your element is in the last level of the heap, right, in the leaf level, right? So how many elements would be there? Around order n elements. So n by 2, that is order n element would be there. And you have to search through all the order n element. So therefore, searching in a heap is order n time, which is nothing better than your array. You could have done, I mean, it's actually worse because if it is a sorted array, then you can do a login search by applying binary. Right? So yeah, that's the problem. So heap extract bin was taking my login time. Heapify was taking login time. Time complexity of build heap would take some time to discuss. It's there in the lecture. After your exams, I would request you to just go through the lecture. And then in the next class, when I explain the algorithm, I mean, Dijkstra and Prince algorithm using the heap, right, line by line. Before doing that, I would discuss the time complexity of build heap. Now it seems very much easier, right? However, we did not do anything fancy in build heap. What did we do? In build heap, what did we do? We just had a build heap method. In that, we had a for loop. That for loop started from I equal to that n by 2 minus 1 thing, and it went to 0. I was decreased each time by 1, and we were calling heapify. Alright. So basically, this was your whole method. So this loop runs how many times? Order of n time. N by 2 to 0. So that is basically order of n by 2. That is order of n time. And we know that what is the complexity of heapify? We know that it's log n time. Right? So order n time, I'm calling log n time work. So it would be in log n time. So it is quite intuitively n log n time. But the thing is, build heap actually takes order n time work. Okay. Build heap actually takes order n time work. This part, why it, I mean, just by seeing the algorithm, it seems that it is order n log n, but it actually takes order n time. Likewise, I have not discussed the union, union find data structure. That also we will discuss in the next session. So the union find data structure, that also there is a little bit of trick over there because you just like this. So here it seems the complexity is n log n, but it is actually order n build heap. In union find data structure also, it would seem the complexity is order of n square or n something else, right? But the complexity would be actually order of log n. Okay, so it doesn't matter. What I mean is, in both these cases, build heap and in case of the union find operation, both these scenarios, the time complexity is not like it looks, fine. So we would actually have a very new discussion on that topic that up till now we were just following the code to understand how much time it was taking. We were multiplying, we were actually segregating each operation separately, right? Here we segregated heapify and told that it takes log n time. Then we saw that for loop segregatedly, this for loop takes order n time. And then we multiplied. But this might not be a good approach to, in actually analyzing the time complexity of algorithm, that we are segregating each operation and finding separately the time taken by each of these operation and then finally multiplying them to get a result. So this might not give you a proper complexity analysis in some situations, and we would learn about a specific way of finding the exact or a much more tighter analysis of running time, and that's what we call the amortized analysis. Okay, so that these two things, that's why I did not discuss union find at first. Union find and this particular build heap concept, these two would have the amortized analysis concept. So we would discuss that together in the next session. Fine, along with the Dijkstra and Prim's code with the heap. Right, now you all know the intuition by now that why the heap is used in Dijkstra and how it is being used. Just that line of code is omitted, right? But we would once discuss the whole line by line code using the heap with an example. Fine. So main intent for today's session was to discuss the heap properties and heap operations. So all the heap operations we have discussed. By the way, extract min was log n, p5 was log n, build heap is order n. We would discuss that next day. Insert, how much time? You are actually traveling towards the height, right? So you insert at the last level and then you check with this node, then you check with this node, unless and until you get a parent which is smaller or you actually reach the top. So in worst case, you can reach the top, right? So again, how much time does it take? Order of h, the order of height. And we discussed that order of height is nothing but order of log n. So this insert is also log n. So insert is log n, heapify is log n, extract min is log n, build heap is order n, search is order n. Okay, so these are all the operations of heap. Okay. Thanks a lot, everyone. That's it. We would have one more session. We would communicate with you when that session is in the next week. For week 6, I mean.